Okay, good afternoon. I am going to start my today's session, and the session today's topic is about uh, test of significance based upon Z test and T test. Now, first of all, I shall discuss Z test, and for this, the assumption which has been made is that the sample size of the sample from which the population has been drawn is a large sample, and it is large sample because the size is considered to be greater than 30. My today's situation, based upon which I am going to test the significance level of the hypothesis, is about testing the population proportion, or you say some kind of percentage which is given on the population you are studying. Say, for example, if you are going to the newspaper nowadays, probably you have seen that various vaccination, various institutes, medical institutes are preparing, are trying to prepare the COVID-19 vaccine, and they are declaring, and I can see on each day, in the newspaper, that the different companies are declaring that their vaccine is effective. This percent of effectiveness for their vaccine. So Pfizer is saying that his vaccine is effective 90%. Then it, after 2 days, it became 94%. Then another company, Moderna, is saying that its vaccine is actually effective 94% effective. And Oxford AstraZeneca is saying that their vaccine is effective 70%. And today I have seen in the newspaper that Sputnik, the Russian vaccine preparation company, they are saying that their vaccine is 95% effective. But in none of these news, I didn't see the total number of samples on which they are actually testing the testing their vaccines. I do not have any idea. We do not have any idea about what is the sample size they have taken, what is the population. Is the declaration about the percentage of effectiveness is the declaration, is the percentage related to sample percentage, or is it related to population percentage? That is also unclear to us. So here I'm going to talk about population proportion. That means if we assume that a population percentage is given, then how can we test that this population percentage is true or it is false? How can I test it? So therefore, for this particular situation, we shall assume a particular specific value for the population proportion, say P0. P0 is the value of the population proportion, small p, and we are going to test whether our population proportion is actually P0 or it is less than that, against the alternative hypothesis that it is greater than P0. So, and in one of my earlier classes, I already told you that depending upon the sign of the alternative sign present in the alternative hypothesis, we declare whether the test is one-tail test or two-tail test. Now, as you can see that in the alternative hypothesis, the greater than symbol is there. So this particular test is a one-tail test. But there is no hard and fast rule about whether you are able to include inequalities in the inequality in null hypothesis or not. In null hypothesis, you can include the inequality just like I have included, but the equality sign must be present in the null hypothesis. So if you want to write P is if you want to test that your population proportion is having value P0, then you can write P is equal to P0, or P less than or equal to P0, or P greater than or equal to P0. So if it is a matter of equality, then equality must be included in the null hypothesis and not in the alternative hypothesis. But if you ask me, why is it so? Why equality sign should always be present in the null hypothesis and not alternative hypothesis? The answer is that the hypothesis testing tool, which is being deduced or which has been deduced on the basis of this situation, the test is based upon null hypothesis and not alternative hypothesis. So you see below, probably you can see the green colored formula which I will be using for this type of situation. You see in the formula small p is present. So if this particular formula Z is being tested under the assumption of null hypothesis. Okay, so it is the rule. So if you do not include equality sign over here, if you don't say that P can be equal to P0, then you will not be able to substitute the value of P in this particular formula. And therefore, null hypothesis always includes the equality sign. To test the population proportion, we select a sample, a random sample of size small n, and that size is considered to be greater than 30 over here. 30 is the limit above which we shall consider that to be a large sample, and below which we shall consider that to be a small sample. Capital X is the number of items present in the sample who are satisfying the characteristic of the population. So for example, if I say that we know that 50% people nowadays actually smoke. So that 50%, this is my assumption. That doesn't have any base. But this 50% value is actually, I'm talking about the half of the population. To test this percentage, I have to select a sample of some size. Now, if I select a sample of say 25 people, then I will ask each of these 25% that whether he is smoker or not. And I have to rely on his statements. People may lie also. If my sample consists of students, then the student may think that the teacher is asking me about this question, so I must lie. I smoke. Personally speaking, I sometimes smoke also, but I don't say it at my home. You know the reason. So yeah, when we don't say about the absolute truth, but the experimenter must rely upon the subject, whatever he is saying. So suppose my subject is saying, I'm asking my subject, do you smoke? Do you smoke? And there, out of 25 people, only 10 people responded with yes. Then that number 10 is my capital X. Okay, and a small p is the probability with which I can get this success of getting 10 smokers out of 25 respondents. Okay, so this is my small p. This is called probability of success, and you already know that under certain circumstances where the sample size is known, the probability of success is known, the random variable capital X is supposed to follow the binomial distribution. And if we know about the distribution, then, and if we know that it is binomial distribution, then expectation of capital X will be n into small p, and variance of capital X will be npq. These things are known to you. We have done problems on that, and we have also deduced it. Now, we want to standardize the variate. So standardization formula has also been told to you earlier, and it is given by x minus mu by the standard deviation. Here, mean is NP. So I'm writing NP over here, and the standard deviation is root over NPQ. So we get our formula of Z. Now, to test this particular hypothesis under this situation, we will take the help of p-value. And in my last class, I explained what p-value is. So if you have missed my class, you can go through my YouTube video once again, and you can see where I did some kind of board works over there to explain students what p-value is. So here I'm going to take the help of p-value, and which will be defined under the present situation as this. Probability of capital X is greater than or equal to small x, where small x is one of the all possible values of capital X. And we assume that this capital X is binomially distributed. Null hypothesis should then be rejected at any level of significance greater than or equal to the p-value. Now, your p-value is defined in such a way that the statement which I have colored over here in blue color, this statement is actually been taken from the definition of p-value. So the p-value is saying that you have to be careful. You have to be careful enough to choose your level of significance. If you select a level of significance greater than the p-value obtained for the present situation, then you have to reject your null hypothesis. Otherwise, you can accept your null hypothesis. Okay. So we take an example which is given over here. The example says that a noted educator claims that over half the adult US population is concerned about the lack of educational programs shown on television. To gather data about this issue, a national polling service randomly chose and questioned 920 individuals. So you see, this 920 is your sample size, okay? And obviously the sample size is much larger than 30, so we can consider this sample as large sample. If 478 of those surveyed stated that they are concerned at the lack of educational programs on television, this 478 is thus corresponding to the value of capital X. Okay, so out of 920, the responses obtained is 478. And obviously, if you divide 478 by 920, you will get 52%. So this 52% is not the population proportion, but it is the sample proportion. We are to test whether we are to prove the claim of the educator. Okay, what is the claim of the educator? The claim is written in the first line, that half of the adult US population is concerned about the lack of educational programs. Half of the US population. So that half is your population proportion. Okay. From where did they obtain this particular data? Half. This is obtained from various sources, and this is the assumption of the educator. This particular assumption has no base. The particular educator in this particular problem is believing in this fact. Some other educator may believe that this percentage is not 50%, but more than that, 60, 70, anything. So this half, this quantity is your population proportion. And we are going to test it by the above formula. So under the null hypothesis is obviously written in this particular form. It is already stated above that H0 will be P lesser than or equal to 0.50. 0.50 is the specific value P0 against the alternative hypothesis H1, which is P greater than 0.50. And if I apply the formula of P value over here, you see what is happening. We know the P value is given by probability of capital X greater than or equal to small x. Now, if I divide this quantity NP naught from both sides, and if I subtract the quantity NP naught from both sides, and if I divide by this square root term, the inequality will not change because the square root term is positive. Okay, so variance is always positive, and hence standard deviation is positive. And you know the left hand side is nothing but the formula of Z, which is the formula of the standardized variable. So we are replacing this quantity by Z, and on the right hand side of this particular inequality, I'm putting the values. So X has got its specific value 478 corresponding to the problem. Small n has got the value of 920, which is the sample size. P naught is the population proportion because half of the US population we are concerned about, so it is 0.5. And Q naught is 1 minus P naught, so that is 0.5. Ultimately calculating this quantity, we get probability of Z greater than or equal to 1.18. And you know that if you consider this event to be a bar, probability of A will be 1 minus P a bar. So 1 minus P of Z less than 1.18 is written. Why have I transformed this probability into this form? It is because of the statistical table, which I shared with you yesterday in the Google Classroom. The statistical table, the Z table, the values are actually set for this particular thing. And if you ask me what is this, I'll say that you know the probability distribution function of Z, which is e to the power minus half Z square. Okay, so if I want to integrate this from minus infinity to this particular value, 1.18, you can do this integration using Wedel's rule, trapezoidal's rule, Simpson's 1/3 rule. So if you want to integrate it, you can test it by yourself, or you can ask your the mentor who is actually responsible for numerical methods course. that is this particular probability can easily be calculated. You don't have to take the help of the statistical table. But in probability course, we don't have much time of doing this numerical calculation, so we take the help of the statistical table. And that is provided in the statistical table, which I have shared with you in the last, in yesterday actually. So from there, I got some value. As far as I can remember, the value was 0.88 something. And once I subtract this value from 1, we get 0.119. So this is my p-value. And if we set my level of significance at 5%, now you see the level of significance can be set at any value. You can set it at 5%, you can set it at 25%, you can set it at 10%, you can set it at 1%. But once I told you that level of significance, the most preferable value for the level of significance would be 5% and 1%. The reason is very simple. When I talk about the level of significance, then that means I'm talking about the probability of type 1 error. And probability of type 1 error means your values are falling into the critical region. So level of significance in another way is related to the critical region. So if you choose your probability related to the critical region to be 5%, that means your confidence limit is 95%. If you think about the normal curve. Or some people may take the level of significance to be 1%, that means he's 99% confident about it. So it is said that it is most preferable, much preferable, if we consider the level of significance at the value 5% or 1%. So for the sake of my current study, I have chosen this level of significance to be 5%. That means 0.05. And this 0.05 value is much lesser than 0.119. And according to the rule which I stated above, this null hypothesis, the rule about drawing conclusion on the basis of the p-value, the null hypothesis would definitely be accepted. And we shall agree with the educator that yes, half of the population, whatever they believe about this particular claim is true. So thus we can take the help of the p-value and we can give a conclusion on the basis of the hypothesis set on the situation given in the problem. This particular problem has an alternative approach, and this alternative approach you can avoid it, or it is also sometimes very useful. So I'm just stating this alternative approach for the sake of completeness. It is nothing but important, but it is talking about a continuity criteria. So you see that whenever we talk about probability of x equal to I, there is a specific value of capital X, the random variable capital X, you can make it continuous by using this formula. Probability of x equal to I by continuity criteria is similar to this expression. So I can write probability of x equal to I to be probability of x lying between I minus 0.5 and I plus 0.5. So here in this particular problem, if we are concerned about probability of x equal to 478, then you can make it continuous by using the continuity criteria. So previously I wrote probability of x greater than or equal to small x as probability of x greater than or equal to 478. But here also by using continuity criteria, you can make it as continuous, like you can subtract 0.5 from 478. And thus we get 477.5. Rest is same. You can subtract the mean and you can divide by the standard deviation, and ultimately we'll get a term like this, approximately equal to 0.125. 0.119 and 0.125. If I take up to second place after decimal point, then these are very much similar to one another. So conclusion drawn previously with respect to the previous approach will be similar to the conclusion drawn with respect to this approach, because the values are pretty similar to one another. So here also we'll say that the null hypothesis under the given situation will be accepted. Okay, so we are actually agreeing with the educator's claim. Next comes the t-test for the mean of normal population case of unknown variance. Now you see the students, I must say that these different situations you have to recall it, because hypothesis testing is not a universal rule which can be applied to each and every problem. That means a particular formula, one unique formula which will be applicable to each and every case. No, it is not like that. The basic setup that you are going to set a null hypothesis and we are going to set a statistical tool, and then you are going to put your conclusions on the basis of your calculation, that basic set of algorithm will remain same, but what will change is the process of is the statement which will be put under null hypothesis and the statistical tool which will be used to do the calculation. Here the situation talks about testing the mean of a normal population, but if you can remember that mean of the normal population has already been tested earlier. But in that case situation, the sample size was large. Here I'm talking about the small sample. So I have make a note over here that there are two situations. One situation, if the sample size is less than 30, you can take the help of t-test to do this kind of testing. Okay. In previous case, we used the jet test. And also there is another situation in the previous class. If you can recall, if you have the question with you, you will find that in the problem, the population variance was, the value of the population variance was assumed or was known to us. But here is a situation where population variance will remain unknown to us. So if it is so, then also the t-test is much applicable. T-test can be applied. What is t-test? The basic criteria of setting the null hypothesis for the earlier case of testing mean of normal population, and this case will remain same, that if we population means assumed hypothetical value is given to us, we will consider it to be true, and we'll set this as a null hypothesis against the alternative hypothesis, that mu not equals to mu naught. Okay, and as you see, since I am writing mu not equals to mu naught, that means there comes two possibilities. One possibility is that mu is greater than mu naught. Another possibility is that mu is less than mu naught. So two tails are open, and therefore it is called two-tail test. What is important is the fact is that we do not know if we do not know the population variance, how can I use the formula? If you can recall my previous my previous example, you will find a similar type of formula as I am showing over here. What was the formula? The formula was like this: Z is equal to x bar minus mu naught by sigma by root n, and sigma was the population standard deviation. But here, as the case is stating, the population standard deviation is not known to us. So we have to estimate the population standard deviation with some quantity, and the quantity is given over here. It is capital S. Capital S is considered to be the means sample standard deviation. Not mean, sample standard deviation. But there is a very important part which you have to put a tick mark, or you have to make a note about this particular part is, I am not dividing by small n, the sample size. The rule states that if I divide by 1 lesser than the sample size, that means if the sample size is n, and if I divide this quantity by n minus 1, this capital S is becomes the best estimate of the population standard deviation. And if you divide by small n, maybe values are very negligible, but if I divide by small n, the quantity doesn't become the best estimate of the population standard deviation. If you ask me, sir, from where did you stating this kind of things? I must say that as I said, every syllabus has its own gaps. So the gap of your BSM 301 syllabus is that two important chapters are missing from there. One chapter is the interval estimate, and another chapter is the point estimate. If I get chance of taking physical classes with you, then I can discuss those chapters in the physical class. Okay, not in the online class. So otherwise I would have to prepare the notes. Okay, so I'm actually becoming day by day, I'm becoming lazy. Okay, anyways, so if I'm going to estimate this population standard deviation, so I have to and population standard deviation is not known, then I'm going to estimate by this quantity, and then the formula changes only to this type. Previous formula was x bar minus mu naught by sigma by root n, which was denoted by Z, and now the formula has become x bar minus mu naught by S by root n, which is denoted by T. So it's very similar. Okay, and irresponsible students or irresponsible experimenter may neglect this kind of change in the formula. But if you are responsible enough, you shouldn't do so. Okay, so, and if you, and I personally do not prefer any lies in statistic. Okay. And this is the normal curve. It is a very important theorem which is called central limit theorem, and it's said that if you increase your sample size, the almost every distribution tends to follow normal distribution. And also it is kind of a very interesting result that if the sample size is small, then also there is a formula which is beyond the scope of your syllabus, which states that the distribution can be directed to the normal distribution. And once we treat it as a normal distribution, then we get a normal curve, and we set the limits as this at these points. As I'm showing this particular cursor, you see this is the negative number, this is the positive number, and this region, the total of this area and that area will be alpha, your significance level. So this part, this part on the positive side is the positive tail is the critical region, and this side is the critical region. Total area of these two critical regions will be your level of significance. Alpha by 2 plus alpha by 2 gives you alpha. And what is n minus 1? It is called the degree of freedom. Why it is n minus 1? It is because when we calculated the the sample standard deviation, we reduced the sample size to 1, from n to n minus 1. So one particular thing has become negligible or redundant. So therefore, this quantity has been written over here. The degree of freedom is considered to be, degree of freedom means the number of independent variables which is taken into consideration to calculate the values. Degree of freedom is the definition of number of independent variables. Here in this particular case, although the sample size is small n, the number of independent variable is small n minus 1. And after calculating this small t, we take the absolute value of this, and after calculating the absolute value, we compare this value, calculated value, with the tabulated one. In the statistical table which I shared with you in the yesterday, you will find the t table over there. So once we find the value of the t, we take the absolute value of that, and then after this we compare this with this value. If we find that our absolute value is greater than or equal to the tabulated value, we reject our null hypothesis. Otherwise, the null hypothesis is accepted. Okay, so let us go to a problem of this particular situation. The problem is stated over here. Problem number 2 says that here also, you see, I must say one thing, that the p-values formula is given over here, but I'm not going to use p-value to the current problem, because from pedagogical point of view, I have to show you different approach to solve the problem and to draw the conclusion. So now at this particular situation, I'm going to take the previous methodology of drawing conclusion, means this one. I'm not going to take the help of p-value. This will be much more easier to apply. The specifications for a certain kind of ribbon call for a mean breaking strength of 185 pounds. So this becomes your population mean. So it has been stated under null hypothesis. Against the alternative hypothesis that mean breaking strength is less than that. Okay, if 5 pieces randomly selected from different rolls having breaking strengths of this, 5 values are given. So 5 becomes your sample size, and these values are sample values. Test the null hypothesis that mu equals to 185 against the alternative hypothesis that it is lesser than that. Now, when we when we manufacture the ribbon, we try to find its breaking strength, and the mean breaking strength, if the mean breaking strength is assumed to be 185, obviously in the alternative hypothesis, it would be much better if you consider this to be lesser than. We are going to put the ribbon in such a way, we make the ribbon in such a way the mean breaking strength is lesser than that. We don't want to put greater than symbol over here. So that will be kind of you can have mathematically you can set, but it will not be it would not be practical from manufacturing point of view. But although here in this particular problem, this alternative hypothesis, what you are supposed to assume, it is already mentioned. So we have taken mu lesser than 185 at 5% level of significance, and hence therefore my alpha is 0.05. Obviously, since the size 5 is much lesser than 30, so it is a small sample test, and we'll go for t-test. But in this particular problem, your population, no information about the population standard deviation is known. And therefore, we select these samples, we calculate their mean x bar, and we calculate this quantity xi minus x bar whole square. This is very simple. I'm not going to explain it in detail. You know it very well. And after that, by using the best estimate of the population standard deviation as mentioned above, we calculate S by taking the square root, positive square root of this, of the quantity which is obtained by dividing this quantity by sample size minus 1, that is 5 minus 1. And this quantity is coming 8.2191. After putting all the values in the formula, we get a negative value minus 0.506, which is approximately equal to minus 0.551. And therefore, it is mentioned that sometimes as negative values may also come, so you are going to take the absolute of that. Taking absolute value means we're trying to draw the conclusion on the basis of the positive tail of the normal curve. And as per the rule given above, the absolute value of this quantity, that is minus 0.51, will be, and you can take the help of the statistical table, that it will be less than the tabulated value, which is 2.132. In the statistical table, you will find that on the left-hand side column, the leftmost column, the degrees, the various values are given, starting from 1 to up to 30. And on the topmost column, the level of significances are mentioned. So since my degree of freedom is 5 minus 1, 4. So from the leftmost column, I'm going to select the 4, the figure 4, and then I'm scrolling on the right-hand side direction, and will hit the level of significance 0.05, and that intersection point will contain 2.132, this value. And obviously the absolute value is lesser than that, and therefore we must not reject the hypothesis, and we shall conclude, yes, the mean breaking strength is indeed 185. Here I didn't write the conclusion, but you can write it. You have to write it, the conclusion also, in statements in the examination. Last but not the least, my last situation of today's class is paired sample t-test. It's very simple. Here I'm going to draw two samples of same size. Although I have used different subscripts over here. Here for X I have used I, and for Y I have used J. But you see that carefully that the range of I is same as range of J. And apparently apparently you may think that I have chosen these two samples from two different populations. And your assumed population means will be mu X and mu Y. Here you are going to test whether your population means are same or not, or whether they are different. So we set the null hypothesis in this manner. Okay. Now, one important factor is also there, that these two samples are interconnected to one another. This particular interconnection will be clear to you when I will show you the problem. Under such a situation, what we do is that we take the help of this particular formula, which is denoted by T paired. And we take this mean, which is called denoted by D bar. It is the difference of these values, xi minus yi. SD is the standard deviation of these deviations, and small n is the sample size. Okay. And when we calculate the standard deviation of the deviation, again we have to divide by n minus 1 and not n. And therefore the degree of freedom, just like the previous example, is considered to be situated at n minus 1. So once we calculate it, we take the absolute value of this quantity, and if it is greater than the tabulated value from the obtained from the statistical table, we reject null hypothesis, otherwise we accept null hypothesis. Here I'm going to show you quickly that the time is running out, that 7 cars are there. So 7 becomes your sample size. We are interested about the mileage of the car. and mileages increase when we apply some sort of technical additive to the car. So here I have considered 7 samples whose mileage without additive is given and whose mileages with additive is given. So you see, the sample remains same. You are taking the data before the application of the additive, and again you are taking the data after the application of the additive. So the two samples, size of the sample remains same, but the samples xi, mileage without additive, sample yi, mileage with additive, they are paired, they are interconnected with one another. That is called the interconnection. So if such a thing is happening, what is the basis that the two samples have been drawn from the same population? Sample size remains same. What is the reason? How to test the hypothesis that yes, this 7 cars, the car number of cars is 7. You are saying to me, okay, so have you selected the sample from 2 different populations, or are you doing this this kind of things, experimentation on the sample which is drawn from the same population? That can be used by using the paired t-test. And I have calculated everything over here. First of all, I have tabulated the values, the sample represented by I, without additive mileage represented by xi, with additive mileage represented by yi. Their differences is taken and considered to be di. Some differences are negative, some differences are positive. The deviations of the arithmetic mean of these quantities, di, which is represented by d bar, I have calculated it over here, is minus 0.7, has been considered from di. And then we have taken the square of these deviations. Okay. After this, we have calculated the standard deviation by usual manner. You have already know, I have used the previous formula. Just in place of xi, I have used di, and in place of x bar, I have used d bar, and divided by n minus 1. That is very important part, because sample standard deviation of this form is the best estimate of the population standard deviation. So SD is coming out to be 0.9643. And after putting all these values in the formula, we get t paired to be minus 0.7 divided by 0.9643 under root over, under the square root sign 7, and it is minus 1.92. Rest is to take the absolute value of t paired, which is 1.9205. And again, from the statistical table, which I shared with you in the last yesterday, from there, I have got the value at this level of significance alpha by 2 and degree of freedom 6, 7 minus 1, 6, which is 2.447. And since the absolute value is lesser than this tabulated value, I am rejecting my null hypothesis. So this, students, this much for today's class. Tomorrow we are going to, I'm going to show you some other situations on the basis of which we'll be doing hypothesis testing. And I have saved your chat. I have saved the chat and I have noted your attendance. So thanks for joining my class. Bye-bye.